This video, we will discuss an important component of a coherent receiver that is called the phase lock loop. So whenever we are using a coherent receiver, we need to generate a local carrier or a local oscillator that is synchronous to the incoming carrier. So incoming carrier means our signal, right? So this signal could be either AM or an FM signal. So any discrepancy in the frequency or phase of the local carrier with respect to the incoming carrier gives rise to distortion at the output of the detector. So this local carrier must be synchronized to this incoming carrier. Now, just as an example, to explain this further, to explain the concept of distortion, let's see we have a single sideband suppressed carrier signal as shown below. Here, so we have MT here, which is multiplied with cos, and the Hilbert transform of MT, MHT multiplied by sine. So that means this signal is a single sideband signal. So we have two new terms. One is delta W, delta omega, and one is the del that we can see inside the phase of the sinusoidal signals. So what are these two new terms? Delta W represents the Doppler frequency shift. So let's say if the receiver is moving with respect to the transmitter, so there would be some shift in the frequency of the received signal, and the del is the propagation delay, because there's some distance between transmitter and receiver. So there would be a delay that appears as a time in the that appears as a phase in the cosine and sine signals that we have in a suppressed carrier single sideband signal. So now let's say we have a coherent receiver. That means we need to multiply a local oscillator with the incoming SSB signal. So that the product of the multiplication, let's say it's ET, it's given by this expression. So we have this as the SSB signal, single sideband signal, and this is the local oscillator that we have multiplied with it. So after rearranging, we can see that we will have these terms where we have 2 omega C. So these terms are, after the multiplication, these terms are simply band pass filtered. So we are left with these two terms. Now, if the delta, omega, and del, if they are 0, then we are left with MT only, which is the desired baseband signal. But this is not the case generally. So after band pass filtering the high frequency term, we are left with these terms. So in this, if, as I said, if delta omega and del are 0, so the output of the band pass filter is equal to MT, which is our desired signal. But there is, so that this is the case when we have no frequency or phase error, but this is not the case practically. So what happens is we will always have this difference in the phase and frequency, and so the carrier that we have multiplied here needs to track the frequency and phase of the incoming signal, which are these ones, and so that the these terms, delta omega and del, they are as small as possible. So the phase lock loop is typically used, it's also called PLL. It's typically used to track the phase and the frequency of the carrier component of an incoming signal. So it's a useful device for synchronous demodulation of AM signals with suppressed carrier or with little carrier. This can also be used for angle modulated signals as well. So we can perform synchronous demodulation for angle modulated as well as for AM signals. So it has important applications in a number of clock recovery systems. So almost all clock recovery systems use a PLL. So that's why it plays a key role in communication system design. So a PLL has three components. Three major components. First one is a voltage controlled oscillator, that's called VCO. As the name suggests, its output frequency can be controlled by varying the input voltage. Then we have a multiplier stage. It serves as a phase detector, PD, or a phase comparator. So the multiplier stage is the second basic component. And then we have a loop filter, which has a response of HS. We'll see the function of all these three components in the coming slides. So the VCO adjusts its own frequency such that its frequency and phase can track those of the input signals. So this VCO tries to track the frequency and phase of the input signal. So at this point, the two signals are synchronism, except for a possible difference of constant phase. So when it has tracked it successfully, these two signals are synchronized. So maybe there's a small difference of a constant phase difference. And so this phase difference between VCO and input signal can exist, but as long as it is constant, so our, the demodulation will not result in a distorted signal, right? So the issue is if the phase difference is not constant, if it's time variable, right? So the VCO is an oscillator whose frequency can be linearly controlled by an input voltage, right? So if a VCO input voltage is E0 T, so its output is a sinusoid with instantaneous frequency that is given by this expression. So in this expression, omega C is the free running frequency of the VCO. That means if there is no error, if there is no voltage input to the VCO, the output would be omega C. If there is an input voltage to the VCO, which is E0 T, then what the VCO does is it multiplies that voltage with C, which is a constant, and this voltage after multiplication with C becomes frequency. So the range, the range of voltages now are converted into the frequency ranges. So this summation gives us the output frequency of the VCO. So after the VCO, we have the, as we said, we have a multiplier. So what does the multiplier do is it just multiplies the two signals, the output coming from VCO as well as the input coming from the input, which is in the form of the signal AM or the angle modulated signal. So the product is obtained at the multiplier stage. The output of the multiplier is low pass filtered by the loop filter. So the third component, which we said here, it is placed at the output of the multiplier. So the whole block diagram of a PLL is shown here. So this is that voltage controlled oscillator. Input to this is the E0 T, as we saw before. This is the incoming signal where it has an initial phase of theta IT. The product, the multiplier is here. So it multiplies the incoming signal as well as the output of the VCO. And this is the loop filter, which filters the product that exists at this point. So let's look at this from a mathematical point of view. If the VCO output, let's say it's B cos omega CT plus theta naught T, right? So we have just chosen some expression for the VCO output with some random value of the phase theta naught T. So its instantaneous frequency would be the derivative of this phase. So the instantaneous frequency is theta naught, there's a dot above it, and the derivative of this is equal to C E0 T. So this is the instantaneous frequency is actually omega C plus theta naught dot T, where theta naught dot T is given by this expression, right? So now, because where is this expression coming from? We said the instantaneous frequency is the sum of two terms. One is this term and one is this term. So this term is, the second term is written here again, right? So note that C and B are just constant parameters of the circuit from which the PLL is made up of. So let the incoming signal, which is the input to the PLL, be A sine omega CT plus theta IT. So let's say this is the input and this is the output. Now, the analysis that we'll do after this, it's just a general analysis and it's applicable to all different scenarios. So what happens after these two are received, we pass them through a multiplier, as you saw in the PLL block diagram. So the multiplier output can be written in this form. So here we have a high frequency term, which is suppressed by the sum frequency term is suppressed by the loop filter. So the effective input to the loop filter is this one, which is the first term, right? So because let's say loop filter has a response like this, a low pass response. So this term, the one that has the sum frequency is it's negligible, it's neglected anyway. So the effective input to this loop filter is this one, which we have written here, right? So here you can see the input has the difference of the phase of the incoming carrier and the phase of the output of the VCO, the voltage controlled oscillator, right? So now we'll prove that the voltage to the VCO is dependent upon the phase difference between these two, between the two incoming signals to the multiplier. So let's say HT is the unit impulse response of the loop filter. Then we have the output of the filter, the effective output. It's the convolution of HT with the incoming the effective input of the filter, right? So it's convolution between these two because it's in time domain. So the formula for convolution is written here. So we can see we have the change of variables and we have the reversal of HT, which is represented by HT minus X. So the new variable is now dx. So if we substitute this in equation for theta naught t, and we let, because half CB is constant, so let's say this constant is equal to K. So the expression is reduced to this one. So here you can see we have replaced this with theta E, which is the error between the two. And so let's look at the expression for theta naught, the derivative of theta naught, which is over here. So we have substituted this E naught, we have replaced this E naught T with this term. And so this is the resulting expression that we get. So here you can see the theta EX is the phase error, which is defined by this expression. So this quantity is the phase error, which is defined by, which we have denoted as theta EX. So now it can be seen that if there is phase error between, if there's phase difference between the incoming signal and the voltage controlled and the phase of the voltage controlled oscillator output, then we will have some phase angle theta E. If we have this phase angle, then we will have some theta naught T, some value for theta naught T. And that means if we substitute, if this is the value that we are getting for theta naught T, if we substitute, then we have to substitute that over here. So depending upon the value of this theta naught dot T, we will get the instantaneous frequency of the VCO. So if there is no phase difference, then this term would be equal to 0. If we substitute 0 here, the output theta naught dot T, the derivative, would be 0. So that means the PLL is in synchronism with the incoming signal, right? So the block diagram of this whole process is shown here. So this is the phase of the incoming. So this is the effective block diagram of the PLL. We are only considering the phase. So in phase of the incoming signal, phase of the VCO, they at this point, they are subtracted according to this expression. So we get a difference of the phases. So this passes through a sine operator. If there is some difference, we will get some output at this point. If there is no difference, then this quantity would be 0. And so we will get a 0 output here. So that means the VCO does not need to adjust its frequency. So this passes through, it's being multiplied with the some constants. So that include AK as well as the transfer function of the filter that we have. So this is the output which we get, and we apply this output to the VCO. This is in the form of voltage, and we apply it to the VCO. And so that changes the frequency, or in other words, it changes the phase as well. So this process continues, and the phase lock loop tries to lock itself, tries to lock the frequency of the VCO to the incoming signal.